Hello everyone! In this video, we will continue discussing topic 5.4, the magnetic effects of electric currents, and in particular, we will discuss the magnetic force on a moving charge. So up to this point, we have considered the magnetic fields produced by currents and the magnetic forces due to fields on currents. This is in partly due to the historical order of discovery. So this is how things were discovered. But at this point, hopefully it has occurred to you that there is nothing special about current-carrying wires, right? There's a weird sense in which what we have just characterized is super dependent on sort of current-carrying wires wired into circuits and things like that. And that can't possibly be how sort of fundamentally the magnetic force works, the magnetic field works, and as it turns out, it's not. The fundamental phenomenon is simply due to the moving charge that makes up the current. And that's both the field produced by the moving charge and the force on that moving charge. So let's take a look and see how we can use what we already know to inform the answer to the question, sort of, how big is the magnetic force on just a single point charge of size q. So consider our force law, where FB is equal to ILB sine theta, and consider that I is simply the current, and therefore equal to delta Q over delta T. And consider that what we're doing here is we're sort of relating the current through a length L to a single a single charge moving over that particular length L. Given that, you can reinterpret this, and if you slide this delta T algebraically over here, you can interpret L over delta T as simply how fast a certain amount of charge gets from one end of the L to the other. That how fast, L over delta T, can be directly interpreted as the velocity of that charge. And so the strength of the magnetic force is then equal to the amount of charge moving at that particular velocity times b sine theta. Delta Q becomes little q, just the magnitude of the charge moving in the magnetic field. L over delta T becomes the speed of that charge, the velocity of that charge at any particular point, and b sine theta is, as before, the amount of the magnetic field that is perpendicular to the motion, to v. And you might ask yourself, well, how do we apply the right-hand rule? And the answer is very similarly, with a couple of reinterpretations. So instead of instead of current for your thumb, you simply have the direction of positive charge motion. So if this is a positive charge and it is moving in this direction, then your thumb points in that direction. The pointer and index finger point, as always, in the direction of the external magnetic field, and the force that is produced is perpendicular to both of those things according to the right-hand rule in the direction of your middle finger. We'll see a little bit of practice with this in the next video. The final thing I'll mention is that although you won't be assessed on this, it is an interesting question to consider sort of what the magnetic field looks like for that moving charge. And the answer is, well, it's pretty similar to the magnetic field of the current, but it doesn't have that nice symmetry all the way along its motion. What you'll see is directly level with the motion of that charge. You see exactly the same kind of field structure, these concentric circles of magnetic field centered on the moving charge. And as you move further away, the field strength drops. But off axis here, so in this direction, you will also see that field drop as well, just in magnitude as that charge passes. You can think of the magnetic field from this moving charge as being sort of a bubble of field lines or field loops around that charge that moves with the charge itself. And that's not essential for you to know, but because we're considering what happens when you start burrowing down to the most fundamental source of magnetism, which is which are these individual moving charges. It's a good thing to know.